So in our first example, we're going to find the horizontal asymptote of this function. And in order to do that, we're going to set this up as the limit as x is approaching, and in this case, positive infinity. So we'll go ahead and rewrite this. And what we're going to do is we're going to look at the denominator, and we're going to look at the variables in the denominator and determine which is the highest power variable. In this case, we have x squared. This is the rule for a rational function. Anytime that we have a division, especially of two polynomials, but when we have division, we're going to take the greatest variable in the denominator, and then we're going to multiply the numerator and denominator by 1 over that variable. So in creating this product, you notice that 1 over x squared divided by 1 over x squared, that is still 1. That is still a value of 1. It would reduce to 1. So we're not changing the value of this function in any way, but what we are doing is reevaluating it in such a way that we can reduce to find the limit as x approaches infinity. Another thing to keep in mind is that in the very beginning, I said that rule number 6 would come in handy when we were trying to find the limit of x approaching infinity, or more specifically, when we're trying to find the horizontal asymptote. So I said that when we have 1 divided by x, no matter how large the value that we input for x, our table showed that we would be approaching 0. Further, our rule 6 stated that even if we had 1 over x to any exponent, it would still approach 0. So we're going to use that rule such that any value or expression that we have a term with a constant over the variable x, or x raised to a power, we know from our rule number 6 that it's going to be equal to 0. So let's go ahead and multiply this product through our function, and we end up with, and we'll carry down our limit. We're still taking the limit of x as it approaches positive infinity. And now we have 3x squared, and each term is going to be divided by that lead variable from the denominator. So our next term is x over x squared and minus 2 over x squared. And then each term in the denominator will also be divided by x squared and 4x over x squared plus 1 over x squared. Let's go ahead and reduce these. So these reduce to simply 1 over 1, which is 3. This reduces to 1 over x. In the denominator, x squared and x squared will be just 1 over 1, leaving us with 5. Here we'll end up with just 4 over x, and we'll go ahead and rewrite this. So we're still finding the limit as x approaches infinity, and we have found that we have 3 minus 1 divided by x minus 2 divided by x squared over 5 plus 4 divided by x plus 1 divided by x squared. So again, regardless of the numerator being a term that's, being a constant other than 1, even if it's any other value, as long as it's being divided by x, as long as that's happening, we can say that it is going to be approaching 0. So each one of these, if you were to build a table, you would find that it's approaching 0. And that means that we are left with our limit as x approaches infinity of 3/5. So what did we find? So 3/5, the limit as x approaches infinity, 3/5 is our horizontal asymptote. So whatever the graph of this function curve does, let's say, and I really don't know, but let's just say that this is 3/8, positive 3/8. No matter what it does in between here, no matter where it goes, eventually it's going to level out, or its end behavior will end up finding that horizontal asymptote of 3/8, and it's going to hug that line infinitely from the left and to the right. So obviously the graph's not going to do this, but it's the end behavior at 3/8. That's what we have found by finding the limit of x as it approaches infinity. Further, because we do not have a variable left, we know that even if we took negative infinity, so the limit as x approaches negative infinity, we still end up with a positive 3/5, and that's probably a little confusing here. So our end behavior is not 3/8, it's 3/5. Sorry about that. So we are approaching 3/5 at negative infinity and at positive infinity. I hope that helps. Thanks for watching.